I hope you had a good break from last week discussion, and so we are here again, ready to continue with our discussion. Now, today's discussion, but before I go to today's discussion, I want to give a recap where we have reached. Our first lecture, we focused largely more about systems and trying to understand what is a system and the components thereof of a system. So we try to reflect on a system and its real implication in a real environment. And we gave some basic examples of what a system is. We also tried to indicate what's the importance of simulation. We indicated that simulation provides a way in which we can represent things in an abstract sense, more specifically, either pictorial or using mathematical way of representation. And we indicated a number of ways in which this has been used and the places where simulation has been used. We then came to lecture number 2. In lecture number 2, we looked at aspects to do with modeling. And we tried to actually say, therefore, this modeling involves a number of abstraction and representation, which is more a continuation of the simulation. And now, once you have done the simulation, so can you abstract this thing? Can you represent these things in a mathematical sense? And we tried to look at different categories of models. And we said broadly, models are based on a high level of, if we broadly categorize at a higher level, we said that they can actually be 2, but we saw below the 2, we can have many. And today I'm going to upload a diagrammatic illustration of that just before the end of today's class. So then we are able to see in a pictorial manner what is this that we are calling the categorization of models. But just to mention, we thought that broadly the first one is what we call probabilistic or stochastic models, those which occur depending on chance, meaning that you can be able to compute or estimate their probability or their likelihood of occurrence. And then we also talked about another categorization, which we talked about deterministic, which we said that this does not necessarily depend on chance, meaning that you can easily assign a value with some certainty. You are sure that this, when it occurs, this is how it will be. And there were examples. And then we said that the rest other moderates will be drawn from there. So today we'll continue the same discussion and try now to bring together what we call the simulation and the modeling component. So today you are going to see the convergence between the simulation and modeling, so that then we are building towards a convergence. So what we are going to look at is therefore workload or computer workload and preparation of its models. Computer workload and preparation of its models. And by the end of today's discussion, hopefully we'll be able to understand the steps of modeling process. We'll then try to compare the steps of modeling process to system development life cycle. System development life cycle, that is SDLC. You may have come across it when you are doing system analysis and design in your earlier courses. So we want to see they do processes, that is modeling process and system development life cycle. do they follow the same pattern, or do they have some similarities or some divergence? So that's what we want to look at. Then ultimately we'll try to look at where do we apply this modeling process. So that will form our first part of our lecture today. And then part two, we'll look at how do we validate and ensure that the models that we have actually come. Because before you actually put something into use, you must actually confirm that it's working. How do we validate that? So that is what we are going to discuss today. So today we have two sessions, the first and then the second part of the lecture. So there will be a break between the first and the second part of our lecture. So we can therefore start. So the first thing they are going to look at, what are the steps of the modeling process? Therefore, use that, then you can actually be able to come up with a model. Even before I go to the various of modeling, so the process of modeling therefore follows steps. It's important to understand that this process follows a number of steps, meaning therefore it's sequential. That's very important. And the first thing therefore one would need to appreciate is that you are modeling because you want to represent something, you want to solve something. Remember, we said the essence of this modeling and simulation is to ensure that you have a way in which you can solve a complex problem in a mathematical form or in an analytical form. So therefore, modeling process is cyclic. Apology, I was at breakdown in communication with my end, network drop. I hope it will not recur. So what I was saying is I wanted to give an example to bring this cyclic nature in modeling. For instance, in the production of like now what's happening, testing of medicine. What happens is that sometimes they produce something, when they reach at the end, it fades. They do not actually say now we give up, they go back to the beginning. So it's cyclic, meaning you will come up with something, when it doesn't, you go back to the beginning. That is the cyclic nature of modeling. It compares closely to the software development life cycle. So remember objective number 2, we are saying we need to compare the steps of system development modeling or life cycle to that of what we want to look at. So please reflect on what you did on system development life cycle. Needless to go into it. Now then, remember, just to mention, software development life cycle starts with that where you are actually saying identification of the problem. You start with identifying the problem. So we can actually also see whether this modeling will also start from the identification of the problem. Then The process is cyclic, therefore, because at any step, one might return to an earlier stage to make revision and continue the process from that point. Quite often we talk about the system development life cycle is iterative, and hence there is the iterative system development methodology, as you are very much aware. So the first step, therefore, in modeling is analyze the problem. Analyze the problem. To analyze the problem is the same as identifying the problem. You identify the problem. How do we identify the problem? We identify the problem by conducting what we call as twins. If you and it exists, you must actually analyze how things are happening. You are asking yourself how things are happening. So you are reporting how things are happening with questions like, why are they happening like this? How are they happening? So why and how? So the key question are the gaps. At the same time, you are also trying to say, is there a deviation from the expectation? If there is a deviation from expectation, then and the deviation is largely negative, we say causing this deviation. If there is a deviation, there must be a cause. Which is the cause becomes the problem. Because when we are now going to model the actually find a solution to the cause of that deviation. So therefore, you conduct a situation analysis to be able to identify the problem precisely and understand its fundamental questions clearly. Like I've said, why, how, and what's the deviation? So basically, have those three questions in your mind. I will put them on the chart for purposes of, yes, I can see, sorry, the screen it's shared. So I hope now everyone is able to see the screen. Yeah, sure. So the screen is now shared, I believe. You should be able to see them now. So yeah, so then the next, in analyzing therefore the situation analysis, for the purpose of identifying what's the problem, you are actually asking why. We can say the first question is what is occurring, right? That's the first question one will need to ask. Then the next thing is why is it occurring this way? Okay. Then how is it occurring? All right. Then the last thing that you ask yourself is what is the deviation? Right? What's the deviation? So if you answer those questions, then you will be able, by the time you reach the deviation, you see the deviation when a system, remember we said a system is really an interaction of components that are aimed at, doing something. Let's start from there. That really the interaction of things for purpose of solving something. So when this interaction does not therefore lead to the solution, that you want, then it means it's a deviation. So then the question is, what is causing this deviation? How did it occur? Why is it occurring? Then from there, you will be able to fully describe the. So that is the starting point in conducting what we call situational analysis. The outcome of, therefore, at this stage is the determination of the problem's objective and deciding how the problem can be classified, right? How the problem can be classified. This is important. It has to be classified. The modeling approach that you are going to use. Say that if the cause I've actually indicated there why it is occurring, if the cause is something which is, let's say, for sure it's known that it will occur, then that becomes something you say it is a deterministic problem. If what is known, the person conducting that experiment analysis not knowing, then we call it is. This is the beginning of a good, rather a good modeling, that you must be able to categorize your work at that particular point that way. The next thing that you'll do once you've known it's either deterministic or stochastic, then you'll move to stage number 2. Now, in stage number 2 is to formulate a model. Create a model, meaning can you your problem in a manner that by a modeler. So in this stage that you will do in order to formulate a model, number 1 is to identify the goals to initiate a simulation study. Identify a specific set of goals to initiate a simulation. What is a set? What do we mean by a set of goals? Now, remember, the thinking here in simulation or in modeling is to represent a situation, something which is occurring. And that's why I talk occurrence, occurring in the various questions that about occurring to ask yourself. Now, occurring, it means something takes place in order to achieve something. So that which is achieved become what we call a goal. That which is to be achieved become a goal. So for instance, if you say, for hypothetical reason, example here, if you say, that occurring various parts of the country, if you want come up with a mathematical model, so you want to predict chance or likelihood of occurrence of floods in a place. You can see I'm already saying likelihood, chance. So given a need to then start asking myself what occurs which leads to something. Example is like heavy rains. So I would say I need to formulate heavy. There is, heavy rains leads to what? So I say heavy rains leads to, surface runoff. for instance, high surface runoff water which is flowing on the surface, which is not seeping into the ground. So, in other words, I will conduct that if a lot of rains, what if it rains a lot? A lot of surface runoff is going to occur. So you see, in this particular case, I'm identifying a specific of the thing that I must therefore capture is one rain, heavy rain. So meaning therefore, if it rains heavily, then runoff, surface runoff is going to occur. Saying of what the percolation or the nature of the soil, which the amount of water that is going to be absorbed by the earth by that particular soil. I need therefore to understand the soil structure where this rain is going to occur. So then I say if the capacity of the soil to retain water is low, it means then a lot will not go down, but then will flow. Such kind of things. So these are quite a number of scenarios, a number of goals that I must set. So that's what you do in identify specific set of goals. Those things that when they occur lead to something, which then now the goals could be for what if analysis. So it's important to put this statement, which is in bold, is very important. What if analysis, which is exactly what I was saying. But if it rains a lot, then what I'm asking then, so meaning that there are conditions here I'm putting, that what if it rains a lot, what happens? So that which happens becomes a goal that I must be able to monitor, must be, the outcome that I must be able to monitor. So if you look at the what if analysis, you can almost try to reflect it to the if statement in programming. The if. So essentially modeling at this particular stage, therefore, to algorithm design and reflect it more specifically the conditional statements, which in this case, let's reflect on the if statement. So I think that, so the goal could be for what if analysis of a system being designed or for evaluation of a variety of prototypical scenarios of an existing system. So it was like whatever I've actually given, I've given two scenarios that when it is a lot of rain, there will be a service runoff. But you can see I've also put another condition that even before the service runoff occurs, then we need to understand the soil structure, because some soil cannot absorb and allow this water to seep to go into the ground, and therefore mitigate this. So when you start thinking that way, then you are logical, and therefore that informs the formula that you are going to come up with. Now, at this stage, therefore, the performance measures of the system being studied must be made explicit. What do we mean by performance measures? You can see, like I'm saying, heavy rain. So meaning that heavy rain, I can measure it. I ask you myself, what is this heavy rain in which can cause? Then I also talked about what I'm talking about, soil carrying capacity, soil water holding capacity. See, soil water holding capacity, I can measure it. So meaning that when you are therefore at this particular stage, putting these conditions, you are asking yourself, how can I measure this? Can I measure it in quantitative or can I measure it in qualitative? And I must state here that it's not always that you are going to measure them in terms of numbers. I believe of you who are in this class, I suppose everyone here, you did artificial intelligence or an introduction to artificial intelligence. So in other words, in that particular class, you must have been introduced to basic, analysis of both quantitative data and qualitative data. Those qualitative data expressed in terms of, sentiments, words, and second of things. So you can also formulate, therefore, statements that can actually be reflected using what we call sentiments. But for purpose of this particular course, we will focus on quantitative aspect, right? So just to make this clear, like example I've given, I'm talking about amount of rainfall, raining every. So I ask, okay, raining every. How do I measure rainfall? I can measure it in millimeters, and then therefore it is a quantitative manner. If I'm looking at the soil capacity to hold water, I can also measure it using other measures. The outcome from this stage is a design of the model, forming an abstraction of the system. One is modeling, meaning is a designing of a model. In other words, a way in which you are representing it in basic, either both graphical, and I would encourage you to start with representing. You can represent it as in a diagram by actually saying water is coming, so it passes through soil, some will pass through, and such kind of things. But you can also represent it using a mathematical way. So that's what we are saying, an abstraction. You are not going into to show how the soil is holding, but you are aware from science that soil can hold some water and some will go. Hold some water, that becomes in the next stage of implementation. The other activities, therefore, you will do in this particular stage. In this particular stage of formulating the model is you gather, do gathering data. So in gathering data, you are actually correcting the relevant information. So you create this one now. If you look at the first stage, you can do system development life cycle. Now, stage number 2, always in system development life cycle, will be now requirement gathering, which is the same as what you are saying here, gathering data. Meaning, if I'm saying that I need to model and to predict likelihood of raining, and therefore if it rains, it causes floods, I must actually have data. And so having known that I need, at this particular stage, having known the various goals, I've set my what if, then I must correct data on those measures. And these measures, we call them variables, as remember what you talked about, state variables. So I correct this data using the correct measure. And there are many methods that one will use to correct data, but I leave that for you. But what's important is we are saying collection of relevant data will assist in obtaining information about the system's behavior. Remember, we also talked about system behavior, which therefore forms what system behavior gives you what we call models, which is the same as what you talk about business rules in database modeling. Is formulate simplification, documenting them. Remember, there has to be system, there has to be assumptions. Every formula example, the one I'm giving, you see, I must make a determination and an assumption that the amount of rainfall becomes heavy when it reaches a particular threshold. Becomes a specification, so that then when I'm going to code, I'll actually say if it exceeds here, then this occurs. Otherwise, if I don't, I will not actually be able to be doing a good modeling. Then the assumption, perhaps if I'm looking at the soil carrying capacity, then I'll actually get to know that what the assumption I'll make is that what is occurring as service excess of what is held. So that becomes an assumption. It's a valid assumption that what is held, in other words, runoff, what is held can't flow. So I want to take, and then others will actually say that the speed of runoff is dependent on the gradient, meaning therefore gradient becomes something that I'm going to control and then try to see if the gradient changes, what is the rate at which runoff is going to occur, among others, assumptions. And those ones sometimes in advanced levels we call them structural assumptions. But at this level, I want to put it clear that there must be something that you assume. But let me give an example which you may relate a little bit better. When you were doing, I'll take you a little bit back to your high school, not very far. I believe you can remember a few things there, either in chemistry or in physics. I believe majority of you, or if not everyone here, did chemistry. You in chemistry, like industrial processes, you are trying to conduct experiments in a specific environment. And so that conditions that the environment had to fulfill were experimental aspects. Meaning that you are actually saying that the outcome of my experiment is dependent on the assumption. If you are doing heat transfer or calorimetry, I don't know which word you made. When you are dealing with those substances, you are eating, substance, and then you are, let's say, metallic substance, you could actually heat it and then transfer it into maybe a particular liquid and then check to see so the assumption that you made was that when you removed that substance from wherever you were heating it and transferred it water can or whatever a liquid container, you were imagining and you were clear that there never occurred some heat loss while you were that is an assumption, but there could be a reality if you are moving something from where it was being heated and then you are transferring into a liquid in another container. Even if it's a minute or rather a second, there will be some heat loss. But then the assumption here, you are saying there's no heat loss. And if there was, then you are actually saying it was not so significant to the extent that it will affect your model. Such are some of the assumptions you take. So you reflect, and it must be, the assumptions you take must be reflective on the conditions that must be fulfilled for your model to work, for your formula to work. The next thing here is model abstraction. This is model abstraction is really writing an equation, and I'm sure I can been doing model abstraction since very, can I say, since primary. Some will be like, no, you have never done abstraction. But the reality is, if you reflect when you are doing questions like the age of the son when added together is this, and the age of the father is this, what's the age of the, and you could start now saying, oh, let the age of the dad, the son, something. So that is what we call model abstraction. In other words, I put these things together and then see how they interact to give what I need. So the next thing that you do in this again in model formulation is determine variable and the units, which I think I've mentioned up there, conduct the measurement. So you must actually get to know which are these variables and how are these variables going to interact. And sometimes it's important you recognize that you might not measure as given something that you've done, but I would nonetheless again remind you, first subject, rather first topic in physics, in Form 1, I think, and yes, physics. You talked about specifically there are basic units and the derived units. For instance, you could say that basic units like distance, we measured using a basic unit called meters. But then you went ahead and actually said, I can obtain area. Then you start say area is measured in, maybe meter square. So in this particular case, you are actually saying, okay, meter square is derived because you obtain it from a basic unit. That is what is implied here. That you try to see what's the relationship among the variables and the submodels, such that if I am to get the area, I first need to obtain what the distance. So there is a relation between area and distance. That I cannot get area if I don't get what? If I don't get the distance. So that is the element. What we are saying, determine the variables, ensure you understand their relationship, and see how they behave and how do they affect one another. But more importantly, determine equations and functions. Are there things that can relate them? And for you to do this, you again go back into, I think you are topic number 2 in Form 1 mathematics or something like that. If you have forgotten, I'm trying to give you a clear picture that what you are doing is not unique, is not different from what you have done, but it's only that you are trying to put so many things together. If you remember, you did a topic called expressions. And then from expressions, you went to what you were calling questions. And later on, you started looking at functions, maybe in second year, rather in year 2, no, what do you call it, in Form 2. But at the same time, in the university setup, in the first units of mathematics that you did, there was a mention about functions. What does that mean, therefore, in the context of what we want to do here? We are saying, okay, I have known my variable. Let's say my variable is x, and I have also known another variable is maybe x squared. All right. Then I want to ask myself, what's the relation between x and x squared? So when I know what's the relationship, that the relationship is expressed in terms of an expression or in terms of an equation or in terms of a function. For instance, you can, so for instance, in that particular case, I can actually say, I can say if I know x, nonetheless, this can't edit, but in future, put a different. Then I want to know, okay, these are my variables. What is the relationship? I will then x squared. I'll say now x squared, even in here, is equals to x multiplied by x, right? Such that that is what I can actually say. So then I can say maybe, all right, please, you can check on the chart. I'm trying to write something there. That means, therefore, I can say a function. I have a function called, I can write a function that is x squared is x multiplied by x. So meaning with this, I have started doing my modeling. So in that particular case, therefore, I am putting what I call equation and a function. So then I reach somewhere, I say let x squared be, so let x squared be, let's say, be k. So when I say let it be k, I'll say then I can say k is equals to x like x multiplied by x. All right. Or I will say it is now I'll write it. It is k is equals to. So here then I'll say f of k is equals to x multiplied by x, like that. So in that particular case, then I have built what I say an equation. But you see, I started by first of all doing what? Understanding my relationship, and then going through this. But then there is the other thing that is here, units. Now, units becomes very important, because if I don't have units, units must be consistent. You very well know in programming, if you have an integer multiplied by a character, it can't work, right? There will be type mismatch. If I have an integer multiplied by an integer, it's okay. If I have an integer multiplied by a float, I must be able to again provide, a way of ensuring the precision is not affected, right? So the same, if you reflect those things, is what's implied. Then the next stage, what you do in that formulating the model is to solve the model. To solve the model is like trying to, okay, how can I obtain, for instance, if I need from here, we can actually say, if I needed to find k, how do I obtain it? If I needed to find, is really reflect this when you talk about making the simplest way is, how do I obtain one variable from the starting point? That's number one. Number two, if I have a particular model, what are the techniques for solving that equation? Now, most of the models that you are going to look at, I'm going to talk about ordinary differential equations. Ordinary differential equations, some may be in the form of what we call system of equations. Then we start actually saying, okay, how do I solve system of equations? Or if I have my equation is a form of a quadratic, how do I solve a quadratic equation? So to solve the model here, you must determine how you will obtain a solution for the various variables of your model using standard procedures that are there. So once you finish with that, the next thing you will do is the model implementation. The model implementation is now you are able to solve. That means you can obtain values for the various parameters or the various variables of your model, like you are obtaining X, you are obtaining a value for Y, your equation has this. Then now you use those to be able to predict. For instance, if I'm able to find the amount of water held by the soil, I know the amount of rainfall that is coming. Then once I put all this into my model, I can then be able to predict. That's what we call basically using the model. And the next thing, once you have used it, you have implemented the model, it doesn't stop there. You must verify and interpret the model. Now, in the verification and interpretation of the model, we will discuss a little more on this in our next chapter. But to verify means you want to, verification is not the same as testing. Verification means expected, right? You see, it must give. That's the question you answered there. Then when it's how do I interpret the result that you get? How do I interpret that? For instance, if I had a model, do I what is which was moving simply because of, you know, in trying to say what contributed. For instance, if I was say floods, I need to ask myself, because there was a lot of rain, is it because there was the gradient was steep? Is it because that the soils could not hold anymore? So I start interpreting each one of the things that I'm looking at. And I'm sure you have actually seen, like now the floods, people would actually say, oh, the occurrence of these floods is because of heavy rainfall. But it's important that people also reflect that there could be human intervention, things like clearing the the forest, which then allows the speed of this to move. I think there's a lot of writing here. The process determine if the solution works correctly. I will explain this. And the interpretation, I will say this. Then there will be the execution. Now, when you have verified that this is working, so now you start making use of it, is what we call the execution. Now, after the execution, will always be output analysis. Now you are using it for purposes of doing what you expect it to do. That is use appropriate. That's what we call output analysis. When we come back, I'll be able to demonstrate what we call by a statistical method and output, real output from some research that I've been doing to demonstrate. Here is where you are actually saying, okay, from my model, this is what I get. But in reality, this is what happened. So that is what we normally say. Ideally, a model will not be 100% in reality, but then there is what we call a degree of deviation that is permissible. Report on the model is another thing that you report. That is, in the report, it must cover all the things that you've done, all those stages. In other words, you are documenting. You document how did you conduct your analysis of the problem. What did you find there? How did you design the model? What solution did you get from your model? What's the result and what's the conclusion? I'll be able to do them. This is really that if I was doing, in fact, this is one of the areas that I hope most of you will find time and write something that you can present during our research week or research conference in November. It will be interesting that when you are going to report, you report in this aspect, that you conducted an analysis, this is what you found out, and from that analysis, you came up with the model, and this model has the following components. The model, use that to give you the solution, and therefore from the solution, these are the results and the conclusion thereof. Others is about that one will actually give. In other words, you want to give a recommendation that the model can actually be used. Okay, so generally, whole aspect about things into perspective. Basically, now this first part of today's discussion was to talk of system, rather the stages of modeling. So it is quite extensive, but this way from the system development life cycle, there is a lot of similarities, but not a perfect. Similarities, but not a perfect fit. That is the. Now I want you to do the. I want to give you a break, and this break is going to be of 1 hour. No, 30 minutes. No, I think it's going to be 1 hour. And in that, you are not going to answer these questions which are here. Compare and contrast modern process with the stick method, make observation, formulate hypothesis, develop a testing method for hypothesis, collect data. That now, in these questions, they are not different from up there. The first one, make observations, is what is in an indirect way of actually saying conduct situational analysis. Formulate hypothesis is where you are actually setting what we call a set of goals. Then once you set the basic models or equations, correct the data. I think that one use the data. Using the data, test the hypothesis, accept or reject the hypothesis. You are trying now to start checking out your work. Is the following. You will pick a situation. So you will pick a situation. So I think I will put that on my. So what I want you to do is, number one is select a situation or a problem, or as an environment. Can I say an environment that can be modeled, like the one I was giving about a situation, and don't know, situational conduct the problem. It's modeling. So that's the first activity you will do in a group that you are going to form. Number two, formulate what if analysis questions or statements that can be used in the model. This one, I want you to reflect like the if statements in programming. Then number 3, you do iterate, convert the what if analysis statements into a set of relationship. And I'm going to say relationship or relationships. It may be 1 or it may be 2. Okay. Number 4, identify the key variables in your, let's say, model in number 3. Because basically, when you are in number 3, you would have actually come up with a model in number 3. So that will be the exercise I want you to do during that 1 hour break. How you can do it, let me not be prescriptive. You guys are innovative. I believe you can innovate better ways in which you can do. But what I'm going to do is to create breakouts. And these breakouts, I'm sure you know, they are usually created randomly. So my apology if you wanted to be in, with your friend. I'm sorry. So this breakout is going to be between 7 and 8 participants. So you will belong to a particular breakout. So the first person in that breakout group is the chairman of that group. So the first person in that breakout room is the chairperson. I will be joining each of these groups independently during the breakout session. So I'll be logging into specific groups to check on what you are doing. So I want to give you some time. So I'll start joining in at maybe after half an hour from now. But so the breakout I'll open. Please start joining. I managed to enter into a number of breakout rooms. If I didn't manage to enter yours, my apology. I thought I had sufficient time, but somehow it was not possible. But for those that I managed to enter, I found that the discussion was quite good and very encouraging, and at least people have understood the science. Basically, what I wanted us to achieve here is really to have that practical interaction with our colleagues to try to appreciate what we are calling this modeling, as it were. But before I just move on into something, I may want to ask maybe Esther Njoroge, if you are there, Esther Njoroge, to say something, and then later on we'll also want to hear something from Jaden Lusek. you are in, please, you will also say something. And then Shadrach Njuki. At least those three colleagues to say something. How did you find the discussion? So we can start with Esther Njoroge. Esther, are you in? Maybe Esther she's not there. Can Jaden? Yes, you can. Thank you. Yes. The second one, how often the discussion was, and of course you can mention what you maybe you say this is what you focus, and overall this is how you felt how it was session. Okay, so you wanted to know how somebody can be trained on how to. I didn't get it. What was the expected outcome? Oh yeah. Oh, great. That's quite an encouraging. That's nice. I think anyone that may assist in. You've seen people trying to climb a mountain and then at the end they never make it, or maybe they experience challenges. That's nice. So I hope I will be hearing more about the same. Thanks, Jaden. So, I think Sadrak, is it that we have many people called Sadrak? I can be more specific about this, preferring Njoke. Njoke, Sadrak. And then Trone Reine. Trone Reine, please go ahead.
For us as a group,
Yes,
discussion was fine. It
yes,
was very all of us participated.
yes.
Should I answer the questions you gave us, or?
Yeah, sure. Yeah.
Oh, okay. We came up with the environment of the forest, where we have forest fires as a problem, and the objects within a simulation of the real life entities. We had the forest guard. We had fluctuations in temperature and fluctuations in motion within the forest that lead to causes in fire, where you have human activities within the forest and also natural causes of fire. That's through the height and temperature. So we determined that the environment should be stochastic in that you can't predict the entities that interact, the time they will interact, and it's continuous and as well dynamic. Then for the what if analysis, we had the independent variables as temperature and motion, and the dependent as the fire and the forest guard that respond to the independent variables. That's the fire and the and the motion. Then when modeling the system, we decided that we should model it around an IoT system where you have a temperature node that picks up temperature and has sprinklers if the temperature reaches a point that can cause a fire. Then for the motion sensor to pick up human activity that can likely cause a forest fire. Then since we have other animals and we move in the forest, you have a drones that actually establish explicitly that the humans in the forest. That couples with the motion sensor. Yeah, that's basically what we discussed. I think that summarizes the 4 questions.
Oh, great, great. I like how we are. And that is the essence of class. The essence is we want to actually this course. Guys, I hear you. I like where we are actually trying to say, fine, there is this mathematics, but that is not it. We want it to, the science you are, which is computer science. So I really look forward to the type of systems that you'll come up with at the end of this a year. That is fantastic. And, the element bringing IoT into this and trying to thank you everyone. Now, I indicated that I was to kind of give a simple illustration of modeling what I'll always be available to share some of these materials. They may exist on the in future. These are papers that I've written that are under review to be used. So I was trying to do what I call modeling effect of meal, exercise, baptize, and stress glucose dynamics. So in this particular case, therefore, you can see meal, exercise, and stress becomes what we call state variables, which also further influences another state variable, which we are calling glucose insulin dynamics. So we can therefore say meal, exercise, and stress are the input, and then these ones here, glucose insulin dynamics, is an output. Now, the thinking, the science that I'm using is what we call gray box analogy. Now, gray box analogy in the science you are is what we normally say abstraction. It's really an abstraction or an encapsulation in whatever way you want to look at it, either through abstraction or an encapsulation. That's the thinking. This is a colleague I was working with. This is Dr. Matt, who's an expert in endocrinology. Juan Vinay, who's Dr. Juan Vinay is a computer scientist. Patan Krishna Swani is we call it Krishna, is one of a known professor of medicine and biochemistry. He has been practicing medicine since 1956. So he's a forest of information. There is Srikanta is a known expert in endocrinology, Professor Srikanta, and Professor Pantanavakanta is a known telecommunication expert. So this is a team we were working to come up with this, and then we came up with something that with is very important because it summarizes the things that you've done that on there, and then I moved there. So in this case, I'm saying that regulating plasma glucose, plasma is blood, glucose levels for both type 1, type 2 diabetics is a challenging task. It's a complex thing. Handling the effect of meal, the exercise, and the stress level will therefore assist one to get to know how do I manage this. But under that knowing how, the questions that I was saying, what? So we built this using what we call Pegerman minimum model. Pegerman minimum model looked at 3 compartments. Therefore, plus K plus M. Those are the three parts. So, but for us, we said, no, we want to pay attention to 12 compartmental models. So we increased it to beyond 3 because we recognize that they are more. Then the science behind it is what we call stochastic differential equation. So meaning, therefore, this is a kind of a probabilistic kind of problem. So you can see, therefore, really in summary, saying, okay, we are actually knowing this is what's occurring. The mathematics behind it is this. And then later on, we actually did. What was important was to show you how the rest of the things are quite complicated. Never mind. This is the pictorial representation. Remember, we said that it's always good to start from the pictorial. In the pictorial, we are saying there are a number of things which are coming in where we are actually measuring. This is a now there's what we call insulin clearance. Some of these things are a bit complicated in this sense, but insulin clearance is that there is, excess. Any excess is removed. But there is what we call here insulin pump. There are those who have they can inject themselves, or they have a pump, which is something which is put on their body, and then it actually gives what we call insulin. Ordinarily, the insulin is supposed to be secreted by the pancreas. So it's not working, therefore you need an artificial, and this artificial is what we call the insulin pump. So when it comes, it pumps insulin into the blood. That's what you are seeing here. There's no need to go on. But when there is stress usually affects. This is what you normally say when somebody is stressed. There's what we call fight to fight. There is that element of anxiety, and the adrenaline moves up. So those adrenaline are regulated by the liver. And that's where you find that if somebody gets a lot of stress and such kind of things, one of the organs that is likely to be damaged is the liver. That's why stress goes to the liver. There's what we call EG, as you are going to see some of these things. So the liver will release a lot of EG. We call some mechanisms to counteract or to give you energy to do this. So you overwork that. Of course, here we are also saying that there is something that can come from the meal. Remember, we had three things we mentioned up there: exercise, meal, and stress. Stress you have seen here. Stress is internal. Meal is external, what somebody eats. Exercise is what somebody does. You can see it's external also somewhere there. So from this graphical outlay pictorial, we changed that into now what we are saying. This is the gray box analogy. In the gray box analogy, we are saying I need data and I need the physiological knowledge. That data plus physiological knowledge is something. What we call physiological knowledge, the state of being of an individual. And therefore, the data is what I correct about maybe the exercise this person has done, the food this person has eaten, the level of stress. And then the physiological is like the metabolic functioning of the body. So that is what basically in an essence. So you can see the equations like the one I was trying to write earlier. I'm trying to say that there is F, which is X now here, like let's say exercise over time, because you exercise over time. You could be maybe meal, you eat meal at a specific time, that kind of thing. But then the equations which informed those things are like this. We are going to do some of this. Never mind. In fact, in our subsequent chapters, I will make these things a bit clear because we're looking at differential equations. These are some of the things that we use. What's important was how, so that becomes the model and mind very advanced levels, but I just wanted to demonstrate. This is at very advanced level. Never mind about it. Just I'm trying to show you that. what I call these values are what we call parameters. In an equation, you will have what we call parameters, the input, like about insulin clearance from the subcontinence. Subcontinence means from the tissue, from the body tissue. It can actually range from this up to this. If it exceeds this range, then there is a problem. So what then happens is we talked about that there are model estimation and testing. In this model testing and checking whether the model is okay, I use what we call maximum likelihood estimation method. I'm not sure whether you did it in any of your probability and statistics course. But then there is what we call the result. I remember I mentioned the other side that you need the result and discussion. So and then I said the result must compare with existing standard. Now, in our result, we had first of all to solve for different cases. If you are having one first case was this, and this we were using patients, real patients. So it's not something fictitious. It's real patients. This was done somewhere outside this country. So so we had to check whether I did whatever we have corrected works, and there is a what we call tester. What we use, what we call ACF, autocorrelation function. Autocorrelation functions are the ones which actually check that does the data that you have really meet the best standards that you need to do. So when we checked graph here from statistical analysis, we were like, yeah, the data is okay. But what's important is now when we are now trying to compare the performance of our model. So what you see in red is how our model predicted. What you see in black is now what we say CGM. CGM, that is continuous glucose monitoring device. This is a device. This is something which exists. These patients had those how do you call them? They had those devices connected into them. So their blood sugar were being monitored continuously. And that's why we call it continuous glucose monitoring. But as we said, you do not have to keep on attaching this thing to an individual. All you need to know is, if you know what this person ate, you can extrapolate and actually get to know how the sugar is going to change. If you know what exercise somebody did, and together with the stress, if you know all these three parameters, you can actually get to know. If you check the way our model is performing, it is taking the same trajectory like that of the device itself. So what that means, it means therefore the model is working. This will now, we need now to move to the next level. The next level is what we call sensitivity analysis. And to do sensitivity analysis, which is what I'm going to talk in this lecture, sensitivity analysis, I need more data so that then I get to see, does the model respond better when the data is large, or how does it behave? So this one was predicted when we are looking at 24 hours. But when we increase the data, you will realize here, ours is in red, the other one is in black. You realize that our model became more sensitive, and therefore was predicting better than the continuous glucose monitoring. And therefore, from there, we were able to conclude that, yeah, this model is good and therefore should be used. Now, where were we going to use it? We are now going to use it in the development of a particular device, what we call a nano device, whereby people can actually be able to use this in their homes without necessarily walking to the hospitals to be able to conduct some of these tests. So this gives us now what we call, this is graphical. Now, when you go into data, I remember I talked about the deviations. Now you can see another output. for type, this is type 1 patient, and sorry, yeah, with this kind of taking them direction as the other one, as the real one, which is going. So you can actually therefore conclude that indeed the model is working. Model that personally built from the scratch. Those colleagues of mine, you try to do some of these things, and then we concluded that the goal of this study was to develop a model for analyzing the combined effect of this. We have extended the Vega model to add these factors, which then becomes something that can be done. So the starting point always is actually saying, so there's something here we are saying by extending. So in modeling also we normally say, I think one group I actually mentioned that they are determinants of something. So what happens is that when you are doing modeling, you must actually be aware that is there any science that says how something should be done in that particular area, how modeling should be done in that particular area. For instance, what the last speaker, his names are a little bit hard for me. I think Reine was that you see, he thinks the rate at which this fire and the issues of fire within the forest are going to be, to spread, or how they're to be contained, we must look at all these factors that they have considered. But the question is, who else has modeled? What is informing that thinking? It's like this. If I am trying to describe how items are floating, I must go back to what we call laws of flotation, so that then understand the science and then I apply the same. And that's like here you can see we had to go to the first founders of modeling this thing called Pegaman. In fact, this is something that occurred 1970s, I think around 1978. But then now you see it has been static over a period of time. Then now we are trying to come up with and actually say no. In his thinking, he was only looking at what we call meals. Now, in meals, is also dependent on many other things. So that is how modeling goes. So I want to stop there and take any question or any clarification from your end. Seemingly there isn't. We are 1 minute past the time we are supposed to conclude our classes, but I want to say what the exercise you are doing as a group. Oh, there is a comment. I think I need to. Yeah, okay. This is a private. I would respond to you shortly, please. So I want you to carry it on at an individual level and then try to reflect on a situation that you can model. Try to come up with something, and you are free to engage me, and then I can be of help if need be. Otherwise, we conclude our class at this point, and I wish you the very best and keep safe, and let's hope things will go on well. On attendance, I'll be updating attendance in the coming week. So please don't worry. I am aware I need to update attendance. I'm not updated due to many activities that were occurring. Otherwise, have a good afternoon and good week ahead.